today, I started off by reminding you of, or when we got to the graphing part, I reminded you of exponential graphs. This is from earlier in the unit. They had 3 characteristics that were common to all of them. They had horizontal asymptote at y equals 0. They have a point at 0, 1, and a point at 1b. And then I introduced log graphs, and I said logs and exponentials were what's of each other? Inverses, right? Opposites. And so that means you take the x and y and you flip them. So for log, instead of an asymptote at y equals 0, where's the asymptote? X equals 0. And it's a vertical instead of a horizontal. Instead of a common point of 0, 1, the point is 1, 0. And instead of a point at 1b, the point is at b1. And the general shape of the log graph is this, for b greater than 1. Okay? And your goal over here, you have these 6 graphs. It's like a bank of graphs, a bunch of choices. You're just going to find which ones match these equations. So you're only going to use 3 of them. And notice that none of these have an actual b value. It just says regular b. It's just generic. But what they do have is transformations, horizontal shifts, reflections, vertical shifts. And so your job is to figure out the shifts that are going on and then find the graphs that match them. But I do want to talk about it a little bit and point out some things. Specifically, I want to talk about 67 and 61 first. What do you notice is the only difference between those two things? The parentheses. And that changes what kind of transformation is going on. When it has parentheses, that becomes an insider's lie or horizontal shift. So that means left 2. What kind of transformation does 2 represent in this equation 71? Up and down, that's right. So without the parentheses, it's a vertical shift. With the parentheses, it's a horizontal shift. That will be one of the first things that students forget to check for on a quiz or test. So be careful about that. Because if you look at 71, it kind of looks like the 2 is attached to the x, but it's not. The x is connected to that log thing, and the only time a number is connected to the x that's connected to the log is if there's parentheses around it. And then on number 69, the 1 right there, the constant, it's not written in the usual place that it is. It's up front instead. So to make the transformations more clear about what's going on in a form that we're used to seeing, we'll just switch those 2 terms. We'll put that positive 1 on the end and put the log here. But the log is negative, so that negative still goes out front. So there's 2 transformations on this one right here. That negative out front means what for the graph? Over the, not the y. It's going to be over the x, because when a negative's out front, it means the output, or the y value, is changing sign. So it would mean if the y was positive, now it's negative. So it's going this way. So it's going over x. And then the plus 1, what does that mean here? Does it mean left 1 or up 1? Up, because there's no what's. Parentheses. So now take a minute and just see, focus on just the 1, 0 point. You know all the graphs in the base function had a 1, 0. Think about how each of those transformations move that 1, 0 around and try to match it to the graphs. You're only using 3 of those graphs. Their answer to 67. Which graph is for 67? Which graph is for 67? Graph 2. That's right. Graph 2. If you didn't write Roman numerals, but you wrote problem numbers, you would have written 67 right there for Roman numeral dos. What did you come up with for 69? 6, absolutely. 6. Or if you wrote the number on the graph, it would be this graph down here. And would you come up with 471? 5. Very good. That one right there. Did anybody get all of those correct? All right, very good, excellent. So that was a quick review over just the basic form of a log graph from yesterday. Okay, so what we're doing today, oh yeah, we're doing logarithms. It's bad, it's really bad. Yeah, it's bad. Any homework questions? No? Did anybody do the homework just as a curiosity? In the back of the homework? Any questions in the back of it? Here's what we are doing today. We're finding the domains for transformed log equations. So for example, we will determine the domain for this function by the end of the lesson, log base 3 of 4 minus x squared. Before I talk about these word things, I want to just set this up for you with some pictures of what we're talking about, where we're headed with the lesson. Yesterday, we had this basic log graph, right? And there's, bless you, tell me an x value on the x-axis that does not have a point on the log graph. An x value with no point on that graph. -4, -1, 0. Is there any negative number that has a point on that graph? No, right? So we could say that for this function, log base b of x, whatever's here, x is always positive, right? It's never negative. And also can't be, what did you say, Paulina? 0. And we're all good with that, right? Those two things? It's true. We're all agreed. That is two characteristics that are true of the domain for this graph. The domain is a set of all the x values. And I can write that in interval notation like this. 0 to infinity. Okay? That would change anytime you shift the graph around. So let's say I didn't have the parent or base graph. Let's say I had this instead, where this right here is -2, 0. Now what happens is some negative values will work. Specifically, anything between 0 and -2, now it is part of the graph's domain. Meaning you could take an x value there and trace it to any point on the graph. So now that the graph has been shifted to the left, instead of 0 to infinity being the domain, it's -2 to infinity. Okay? So our goal today is to find this answer, the domain for transformed functions. But the catch is you're not going to have pictures. Pictures make it easy. Well, all you're going to have is an equation. And you're going to use algebra to figure out which x values are in the new domain. But just know that this is the goal. to find the new domain for a transformed function. So these words up here tell you sort of a bunch of this that I already said. The domain of the parent log function is all the positive x values. We said that. When the parent function is modified, we need to figure out which x values will keep the new domain values positive. It says we're going to use zeros, asymptotes, and test points to determine the new domain. We are going to do those things. I'm not going to call it zeros and asymptotes while I'm doing it, but the basic ideas will still be there. I will be talking about test points. And then we're going to write our solution in interval notation. Interval notation is where you have parentheses, your left endpoint, your right endpoint, and you have either parentheses or brackets, right? That's interval notation. So these are the things we're working with today. But no pictures. Instead, we just are going to have an equation. So here's the base function for this equation is just ln of x, natural log. By the way, do you remember what that is? That's log base what? E, yeah, the natural log. Log base 10 is the common log. So the basic one was ln of x, but this x right here, remember we said already two things have to be true about whatever you're taking the log of. It must be positive and not 0. Can't equal 0. But instead of x in this example, what we're taking the natural log of is this entire thing as like its own little entity, the square root of 5 minus 3x. But the same two things must be true about that, whatever's inside the box. It must be positive and it can't equal 0. So our job is to find all the x's that will keep this not 0 and will keep it positive. We're going to do the can't equal 0 step first by finding excluded values. So we're going to take care of excluded values first. Excluded values means those values that, or what we're taking care of is the can't equal 0 part. Trying to find the values that would actually make it equal to 0. In order to do that, I'm going to take the stuff inside the radical. I'm going to take it out. That's called the radicand. I'm just going to pop it out, and I'm going to find where it does equal 0. Okay. I haven't actually done any math. I haven't got rid of the log. I haven't got rid of the square root. All I'm doing is like I'm taking the stuff inside and trying to do some math on it. I'm saying that stuff inside, that 5 minus 3x, where does it equal 0? Well, I literally set it equal to 0, and I start solving. I add 3x to both sides. I divide by 3. And I get this. X equals 5/3. That number, if I plugged it in, so imagine you put 5/3 for x. 3 times 5/3 is 15 over 3, which is 5. And then what do I have? 5 minus that 5, which is 0. And then I would take the square root of 0, and I have natural log of 0, which it's not defined for 0. So this is one excluded value. We have found one x value that makes the function break. But that's not our only characteristic that we have to talk about. That only takes care of the what makes it equal to 0. Now we have to find all the numbers that will keep it positive and avoid the numbers that would make it negative. And so this is where we do test points. So we're going to do test points on a number line. this is taking care of the must be positive part of the story. So I set up my number line. It's really representing the x-axis of my graph. I just don't need to draw the y-axis to do this part. I know that 5/3 is excluded. And the thing we're about to do you remember in other math classes when you do like inequalities in two variables and you're trying to decide which part to shade? And your teacher might have said, do a test point, right? You do a test point, and if it works, you shade that side. That's exactly what we're going to do here. We're going to pick a number on the left and a number on the right. We're going to plug it in and see if it checks out, if it works. So for 5/3, an excellent number to the left of 5/3 that I always recommend you use if you can is 0. Because it's going to make your math real easy. Now 5/3 is 1 1/3. What number do you like on the right of that we could use? 2? All right, so here's where we begin our testing. When I say to test x equals 0, I mean you go to that highlighted stuff, this stuff I had in yellow, the 5 minus 3x, and you're going to plug that in and see what you get. You're going to say, all right, this is 5 minus 3 times 0, which is 5 minus 0, which is 5. Now, I'm not like, oh, hey, it's 5, yay. I don't actually care that it's 5. I'm like, oh, hey, it's 5, it's positive, right? I'm concerned if that is giving me a positive or negative value on that side of the 5/3. It is positive, so I'm happy. So this side on the left checks out. Any number you picked on the left, if you plug it in, will give you positive. So far, I'm very happy with this side. And now we're going to try 2. I'm going to test out 2. So I plug it in to the radicand. 5 minus 3 times 2, 5 minus 6, negative 1. I don't care that the value is negative 1. What do I care about? The fact that it's negative. Am I happy that it's negative? No. So that part doesn't check out. Your very last step is to write your answer in interval notation. And that is the second thing the number line is excellent for, is to keep your interval notation straight, especially when you have more than one interval. This one's pretty easy. Remember, you need your left endpoint and your right endpoint. What's the left boundary here? And what's the right boundary? I ask and I just write it. It's 5/3. And these both need parentheses. Infinity always gets a parenthesis. And 5/3 gets a parenthesis because it's excluded. It's not an included value. So any x value in that interval would keep your radicand, what's inside the radical, both positive and not 0. Because it's a shifted function. And so it's been shifted that way. You feel kind of good about that? Now we have 2 more examples to do. The downside to these problems is that they're each different. They each have some of their own unique circumstance going on that you have to think about fresh each time. It's not like just a method you can just apply like over and over. Some of it's going to stay the same. Like for example, whatever you're taking the log of still needs to be positive and not 0. But here's what we're taking the log of in this one, this entire thing right here. Okay, must be positive, that whole thing, and not 0. Remember, we take care of the positive stuff with test points. We take care of the not 0 stuff by finding excluded values. But when you have a fraction, there's like a couple things you have to think about. So we have this fraction, and I'm all like, it can't be 0, and you're like, okay. When does a fraction simplify to 0? When does a fraction simplify to 0, Matthew? I like that you said that. That's not correct. But I think what you're going for is the bottom can't be 0 because that's undefined. But when does the fraction simplify to 0? When does its value equal 0? When the top is 0. So there's two things going on here that we have to talk about with the fraction. The numerator cannot be 0 because it makes the whole thing 0, which we're avoiding. So the top can't be 0 because it makes it equal to 0. And then, like Matthew said, the bottom can't be 0 either. But that's because it makes it undefined. It cannot divide by 0. It won't work. So we have two different situations for two different reasons. But both of them give me my excluded values. So here's where we begin, with the excluded values. We set the top equal to 0. By the way, even before, like I technically don't have to do that. It's really easy. What number makes the top 0? 2. But just so you see the math, in case you had a harder equation, really what you're doing is you're setting equal to 0 and solving. So x cannot be 2. What number makes the bottom equal to 0? -3. So x cannot be -3. Identifying those only keeps us safe on the can't be 0 stuff. It has nothing to do with the, well, what will keep it positive? What's the thing we're going to do next to figure out the positive values? Test points on a number line. So this represents my x-axis, my domain. I have these points at -3, 2, open circles because they're excluded. I had to test how many numbers on this problem. 3, right? Because the two numbers break it up into 3 sections. We have to test on -infinity, in the middle, and then positive infinity. What number do you want to the left of -3? What would you like? -4? What number do I like between -3 and 2? 0. What do you want on the right of 2? 3. Now, when you go to test it, you're no longer breaking it up into the top or the bottom. You're going back to the original thing. Because this whole thing, you're trying to see if these x values would keep that whole thing positive or would keep the whole thing negative. So you have to be careful with your signs. So testing -4 looks like this. You put it in for the x's, -4 minus 2 over -4 plus 3. That's -6 over -1. Kind of feels like that makes it a negative. It's not, right? Because negative divided by negative is positive. Does this check or not check? What do I like it, right? I like that as positive. That checks, makes me happy. So then it says 0. It gets kind of tedious at this point, but it must be done. Plug in 0 for the x's. I get negative 2/3. Does that make me happy or sad? Sad, right? That does not check out. And then test 3. Let me do that one a little bit faster. Plug it in. It's positive, yay. Makes me happy. I got 1/6. Try your interval notation for that. Take a moment and try it. There's 2 intervals, right? One to the left of negative 3 and one to the right of positive 2. Was correct. Did you remember the U thingy? The union symbol? He didn't. You did. He didn't. Do I have any straight brackets? No, because negative 3 and 2 are what kind of values? Starts with an E. Excluded, right? And they specifically get parentheses and not brackets. All right. Any questions about that? I have one more problem. Does anybody need this up anymore? That last problem, also a whole new kind of thing. What's in that last problem that we haven't done anything so far with? An exponent, right? But the 2 basic things are still the same. Whatever you're taking the log of must be positive, can't be 0. And what you're taking the log of is this stuff in parentheses. Pauline, are you good? Okay. Also, by the way, see how it says log base 3? Guess how much I care about that 3? Nothing. I don't care anything about that 3 right now. I'm trying to just find domain, the x values. What makes this thing positive and not 0? Excluded values tell me what's going to prevent it from being 0, or what's going to make it 0, either depending on how you're talking about it. So you're going to set something equal to 0. What are you setting equal to 0? So that you can solve for the x's. What are you going to set equal to 0? 4 minus x squared. Whatever you're taking the log of, which is that entire expression. And then you solve. You add x squared to both sides. You square root both sides. And you don't forget your what's that everybody forgets, plus or minus. How many excluded values is that? 2. These are the 2 numbers that when you plug it in would give you 0. And you can't take log of 0. So those are bad. We want to avoid them. So now we do our test points on a number line. The number line representing our x-axis. You take a moment, do some test points, write your answer in interval notation, and see what you come up into your order of operations here. If you don't, you get the complete wrong answer. When you go to plug negative 3 in, You have to square that negative 3 before you do the minus, right? Exponents before minus or subtraction. So that looks like this, 4 minus 9, which is negative 5. Therefore, that whole section doesn't work. This does not check out. If you did your order of operations incorrectly and got positive, you would feel like that was working. Oh, that does not work. We're not happy about that. And then when you test 0, what is 0 squared? Absolutely, right, 0. So that gives you 4, that's positive, hooray. And then when you test 3, you're going to get the exact same thing as you got over there, which was negative 5, because 3 squared is the same as negative 3 squared, and that's bad. So are we going to have a u in here? No, right? Because there's only one working interval, and it's this. And so your final answer is negative 2 to 2 with parentheses. Right? Any questions?